This is challenge assessment 7, the heat exchanger problem by me, Hunter Cassup. The problem is to design a heat exchanger where water is used to cool hot engine oil with a mass flow rate of 8 kilograms per second from 100 degrees Celsius to 80 degrees Celsius. The water enters the heat exchanger at 20 degrees Celsius with a mass flow rate of 2 kilograms per second. And then I'm going to be using the properties from the book in tables A9 and A13 for the oil and the saturated water. And then in this, I'm going to end up determining the area, and then finding all the inlet, outlet temperatures, the effectiveness, the heat transfer rate. And I'm going to be listing all the assumptions that I have to make to do this. So all the given data is the mass flow rate, the three temperatures, and the CPs of oil and the CP of water was from the tables. So the assumptions is going to be steady state operation, negligible heat loss to surroundings, constant specific heat capacity for both fluids. The R of the wall is going to be technically 0 due to a good conductivity and a very thin wall. This is also going to be leading to the areas being relatively the same due to the thin wall and good conductivity. This was seen in the book in chapter 11 towards the end. I'm also going to be assuming no fouling, so that there's going to be no more resistance and heat loss due to that. Step 1 is going to be assuming a counterflow heat exchanger. Step 2, I'm going to be calculating the heat transfer rate. This is just going to be Q dot equals N of the oil times CP of the oil times T oil in times or minus the T oil out. It's going to be calculated in watts. Then I'm going to estimate the water outlet temperature using the LMTD. The temperature of the water out was solved for, and that is the equation you used. And I had to set up this if and else statements so that if the temperature differences are equal, it wouldn't break the loop and it would still work. And this is the LMTD equation used. It's delta T1 minus delta T2 divided by the log of delta T1 divided by delta T2. So then now I'm going to be solving for the area. These are the properties I had to grab it, and I had to assume the temperature of the properties. I used the TF, which is going to be the inlet temperature plus the outlet temperature divided by 2 to get the average of them. And then for the oil, it was going to be 90 degrees Celsius. And then for the water, I got about 62 degrees Celsius for the outlet temperature of the water, I think. And the inlet was 20, so I basically just got like 81 point something. So I just assumed, 41 point something. So I just, instead of interpolating, I just am going to be grabbing the water temperature, or the properties of water at 40 degrees Celsius. Step 4, the initial guess and tolerances for the DH and the L. So I set up an if loop, or a while loop, to get these tolerances, or to get the error down as much as I could to match the best approximate DH and L for the system. This is the beginning. I just started by calculating the cross-sectional area to use that in the V equation, or to solve for the velocity of the water in the oil. Then I used the Reynolds equation. Once I had the Reynolds equation, I had to make sure if it was turbulent or laminar flow. So I set up this neat little equation, if-else loop, to check if it's laminar. Under that, we would use this one, and then else, we're going to be using the Dittus-Boelter equation. I did the same thing for the water. Once I had that, I would solve for the H of the oil and the H of the water. Using that, I would calculate for the total heat transfer coefficient, the U, and then once I had that, I would calculate for the exact area we would need. Now once I did that, I would run another check and just change for the new L and new DH, and I would check to see if it was in the bounds that I wanted for my system, and I'd update the DH and the L, and then I would, if it was not in the bounds, then I would have to run back to the start, and once it broke this loop, it would just end the loop, but it would keep running until I got exactly what I wanted. So then the final calculations, I reran all these calculations to get all of these values for the velocity, recalculated the Reynolds, and then I had to set up another if loop to check that again. Now I'd calculate for the Nusselt, calculate the H, calculate the U, and then I would use all these values that I got from it. As you can see in this table, I got to the effectiveness, and when I was using the effectiveness, I had to use Cmin and Cmax equations, so I solved those here. And then I got C of R, and the NTU was calculated to use in this equation to solve for the effectiveness, and this was a equation that I got from the inside of the book and in the tables that we used in class for a counterflow heat exchanger, and I got the effectiveness of the system to be 0.521. Thank you.